Finally, we see it, the Gorgeous Raptor 3. It's both more elegant and simpler than its predecessors, and any rocket engine on the planet. Clearly, understanding that the rocket engine is the heart of every mission, SpaceX has poured its focus into developing and innovating the Raptor 3, promising to be the king among all rocket engines. So, what exactly have they reinvented? How powerful is this engine, and how does it outshine all the rest? Let's find out in today's episode. SpaceX has achieved an impressive breakthrough with the redesign of the Raptor 3 engine, showcasing a remarkable leap forward compared to its predecessors. We can gather valuable insights from a photo of the Raptor 3 firing on the test stand, shared by Gwynne Shotwell, SpaceX's president and COO. So, how exactly has SpaceX reinvented the Raptor 3 engine? In this image, the Raptor 3 is blazing on the test stand, and the most striking feature is its incredibly streamlined design. Compared to earlier versions, the number of valves and pipes has been significantly reduced, demonstrating SpaceX's relentless effort to optimize and simplify the system. Another standout detail is the exceptionally clean exhaust plume. This indicates a more efficient combustion process, likely the result of improvements in the combustion chamber and fuel injection system. Pay close attention to this. The throat of the Raptor 3 appears very narrow and seems to be smaller than that of the Raptor 2. This is intriguing, as SpaceX had previously increased the throat diameter of the Raptor 2 compared to the Raptor 1 to enhance propellant flow and thrust. It's highly likely that SpaceX has adjusted the throat diameter of the Raptor 3 closer to that of the Raptor 1. The goal behind this change might be to regain the approximately 3 seconds of specific impulse, ISP, that they had traded off with the Raptor 2. With a smaller throat area, the pressure and temperature of the exhaust gases would rise, potentially leading to a higher exhaust velocity and, consequently, an increase in SSP. The point is, where did all those complex valves and pipes go? Here's something that might be entirely new. In previous versions of the Raptor, the igniter in the main combustion chamber was designed with dual redundancy. This means each engine had 2 independent igniter systems. If one failed, the other would ensure successful ignition. However, this approach added significant complexity to the system. It seems that with Raptor 3, SpaceX has made some adjustments to the igniter in the main combustion chamber, possibly reducing it to 1 or even eliminating it altogether. The Raptor engine uses preburners, a crucial component in a closed-cycle rocket engine, where a small amount of fuel and oxidizer is burned before entering the main combustion chamber. If both liquid oxygen, LOX, and methane are preheated to sufficiently high temperatures, their reaction can self-ignite without any additional ignition source. This is because the high temperature provides enough energy to overcome the activation energy barrier for combustion. In this new design, it's highly likely that SpaceX engineers have fine-tuned the preburner process to produce hot gases that can automatically trigger combustion in the main chamber when introduced. The high temperature of the gas from the preburner, combined with the extremely high pressure in the main chamber, creates the ideal conditions for the self-ignition of the primary fuel mixture. So, they could very well have eliminated at least one ignition system. This move not only saves a significant amount of weight and space, but also streamlines the overall design. The gas lines, control valves, and electrical systems required to operate and trigger the igniter have all been removed, resulting in a cleaner and less cluttered design. Additionally, many of the fuel lines have been eliminated, and the remaining ones are now seamlessly integrated into the engine's body. Inside the engine structure, there could be multiple fluid channels that aren't visible from the outside. These channels play a critical role in controlling combustion chamber temperatures and limiting heat transfer between engines. This technique, known as regenerative cooling, is an advanced method in rocket engine design. By circulating cold fuel or oxidizer through small channels within the chamber walls before it enters the combustion process, the fuel is preheated, boosting the engine's overall efficiency. This design has also allowed SpaceX to eliminate the need for additional heat shielding or flame suppression systems. This level of integration has brought about a major shift in the manufacturing process. Instead of assembling thousands of small components, SpaceX now focuses on producing and assembling a smaller number of larger, more complex parts. While each of these larger components has a higher degree of complexity, the overall manufacturing process has been simplified and made more efficient. To produce these complex parts, SpaceX has heavily invested in advanced metal 3D printing technology. Elon Musk, SpaceX's CEO, has even stated, "Indeed, It is not widely understood that SpaceX has the most advanced 3D metal printing technology in the world. This laser 3D printing technology allows SpaceX to quickly create intricate prototypes, speeding up the development and testing process. It's clear that Raptor 3 has made significant strides compared to its predecessor. Weighing in at 105 kilodalton less than the Raptor 2, it represents a major leap forward in reducing the rocket's overall mass. When you factor in the engine, along with vehicle-side commodities and hardware mounted on the vehicle. The total mass comes to just 1,720 kilos. Now let's zoom out and consider the impact of this improvement on a larger scale. For a booster outfitted with 33 Raptor engines, the weight reduction for each engine compounds into a substantial cumulative effect, specifically making the booster up to 38 tons lighter. This is a staggering figure, bringing with it a host of benefits. First, increased payload capacity. With a lighter rocket, more fuel can be carried, thereby extending its range or allowing it to haul heavier payloads into orbit. Second, an improved landing process. A lighter weight means easier control during the landing phases, enhancing precision and reducing the risk of accident, a critical factor in SpaceX's strategy for reusing rockets. Furthermore, one crucial metric we can't overlook when discussing Raptor 3 is its thrust-to-weight (TW) ratio. This ratio measures the engine's efficiency, indicating how much thrust it can generate relative to its own weight. To fully grasp the significance of this figure, let's compare Raptor 3 with one of the most efficient engines in operation today, SpaceX's Merlin 1D. The Merlin 1D has set a remarkably high standard in the industry, with a thrust-to-weight ratio of 184, the highest among all currently active rocket engines. This number reflects its ability to generate immense thrust from a relatively lightweight engine. Now, Raptor 3 is proving that it can stand toe-to-toe with this benchmark. With a weight of just 1,525 kilos and capable of producing up to 280 tons of thrust, Raptor 3 matches the impressive thrust-to-weight ratio of the Merlin 1D. This is truly a remarkable achievement, especially when you consider the greater complexity of the full-flow stage combustion cycle used by Raptor compared to the simpler gas generator cycle of the Merlin. Raptor 3 versus its competitors. Since Raptor 3's official debut, there's no doubt about it. It's the king of all rocket engines. Let's dive into why. First, let's compare it to the legendary RS-25, the engine that once powered the space shuttle into orbit and is now used on the SLS. This comparison will highlight how Raptor 3 represents a significant leap forward in rocket engine technology, a leap that might even astonish the brilliant minds at NASA. Just by looking at their physical forms, the difference is striking. The RS-25 is a massive engine with a complex structure and many components. Weighing in at 3,250 kilos, it's nearly double the weight of Raptor 3. This heft translates to a thrust-to-weight ratio of only about 73.1 for the RS-25, which pales in comparison to Raptor 3's impressive numbers. The RS-25's design is a real challenge when it comes to manufacturing and assembly. It's an old-school design from decades ago that didn't benefit from modern production methods. For instance, the RS-25 has thousands of tiny tubes that need to be crafted with extreme precision, positioned, bent, and welded together, each step done by hand. This process isn't just expensive, it's incredibly time-consuming. As a result, the production pace of the RS-25 is painfully slow. This fundamental issue is one that NASA has been grappling with, impacting not just their budget, but their overall production capability. Aerojet, the manufacturer of the RS-25, can only produce an average of 5 engines a year. This means NASA's Space Launch System, SLS, is limited to just 1 launch annually, regardless of funding. With such limited launch frequency, building an ambitious space exploration program with the SLS becomes a daunting task. Although the Raptor 3 may appear simpler and more compact, it outshines the RS-25 in several critical aspects. The Raptor 3 generates up to 280 metric tons of thrust, far surpassing the 190 metric tons produced by the RS-25. Moreover, the chamber pressure of the Raptor 3 reaches an impressive 350 bar, significantly higher than the 206 bar of the RS-25. It's crystal clear which engine packs more punch, isn't it? Of course, the RS-25 boasts a higher specific impulse, ISP, because it uses hydrogen as fuel. Hydrogen will always have an edge over methane when it comes to ISP alone. However, here's the kicker. Hydrolox struggles with achieving high thrust density. Due to the extremely low density of hydrogen, you need a much larger physical size of the engine to achieve comparable thrust to the Raptor. Just look at how massive the RS-25 is, and let's not forget the legendary F1 engine from the Saturn V. With a thrust of 690 metric tons from a single engine, the F1 was truly a marvel of its time. But remember, that was a marvel from 60 years ago. The F1 design is quite conservative by today's standards, with a chamber pressure of only 68.95 bar and a turbo pump spinning at 5,500 RPM. It generates thrust through a large, cumbersome nozzle design. In stark contrast, the Raptor 3 achieves a staggering combustion chamber pressure of 350 bar. Just think about it. Raptor 1 was at 250 bar, Raptor 2 reached 300 bar, and the Russian RD-180 operated at 267 bar. Additionally, Raptor 3's turbopump spins at over 30,000 RPM, which is 5.5 times faster than the F1's speed. While the F-1 was designed to produce colossal thrust for the Saturn V's first stage, SpaceX's strategy with multiple Raptor engines is to deliver immense total thrust while prioritizing reusability. Now let's turn our gaze to Raptor's most significant and modern competitor, the BE-4. Sure, the BE-4 is undeniably a powerful engine, boasting 250 tons of thrust, but it's also complex and bulky. On top of that, while Blue Origin has only flown the BE-4 once, SpaceX has already rolled out its third-generation Raptor. When Elon Musk unveiled the Raptor 3, the comparison with the BE-4 was virtually settled. The Raptor 3 not only surpasses the BE-4 in thrust, but does so while being a fraction of the size and weight. There's no doubt about it. Raptor 3 epitomizes the pinnacle of modern rocket science, reigning supreme as the king of all rocket engines. What are your thoughts on this engineering marvel? Let's spark a discussion in the comments below. I'm eager to hear your insights and opinions. All right, that's it for today. If you enjoyed this video, please give it a thumbs up and subscribe to our channel for more in-depth looks at the latest advancements in space technology. Thanks for watching, and I'll see you next time.